Hello everyone, welcome back to another exciting video on Blackbody Engineering. In today's episode, we're going to be tackling the heart of our 32-bit MIPS CPU, the control unit. We're going to explore how the CPU decodes all this information through the instructions and how the control unit drives all the control signals that make data flow correctly. Then, finally, I'm going to implement this in Logisim using a simple ROM-based implementation. Why? Because it will allow us to scale it in the future. One of my goals is to allow pipelining, and if I have the ROM, it's easily implemented because I only have to change the microcode of the ROM programming. So recall from our previous discussion, we talked about three types of instruction words: the archetypes, the branches, and also the load and store instructions. We have to understand how the fields of these instructions are divided and how our processor will link these fields to the respective data path in order for our control unit to be able to move data around the CPU. We can start with the simple ones. We can start with our load and store. So recall from our previous discussion, there's three types of instructions. We have the load and store instruction. And that instruction is divided in four spaces: 1, 2, 3, and 4. The first one is 31 to 26 field. The other one is 25 to 21, 20 to 16, and lastly 15 to 0. This is gonna be our address, our RT, our RS, and this is gonna be either 35 or 43. And the way this works is you have your control unit here. This takes the opcode and it reads it. And remember that if we have 3543 for our opcode, then this is gonna send a signal called LEU up to our LEU, and that's how the result will be calculated. It depends what it is. So if we have a 0, 0, then we're gonna add to our from our LEU, and that's gonna be that's gonna be the result here. If we have a branch, it's very similar too. It's gonna be the same field divisions, but then in my opcode, I'm gonna have a 4. The rest is gonna be the same. And this is gonna go to my control unit. That's gonna send an LEU up to my LAU, which is gonna trigger a subtraction. Now, the R type is a very interesting one, because the 32 bits are divided in more fields. So I have 31 to 26, next one 25 to 21, 20 to 16, 15 to 11, 10 to 6, and then finally 5 to 0. And this is always going to be a 0. This is going to be different sources. This is going to be my destination. This is the shift amount that I'm going to shift the result. And this is my function. We do need a function. And the way this works is, this is my control unit. The opcode is going to get fed to my control unit. And then the function is also going to get fed. It's also 6 fields. 1, 2, 3, 4, 5, 6. Actually, no. Yeah, sure. I'll name it F5 through F0 for better clarity. And then a new signal is gonna come out called LEU up, and that's gonna be fed into my LEU control. Yeah, now realizing I made a mistake here. This goes to the LEU control, and then this is the signal that's gonna get fed to the LEU, same as here. That's gonna be fed to my LEU control, and then this is called the LEU OP1. Oh yeah, yes. And that's gonna be fed into my LEU, and depending, so here I will have a value here, I will have a value here. So this is how you integrate the fields into my data path. Obviously, my control unit has more outputs, which we're gonna discover now. So our control unit has multiple outputs besides LEU up. So we have register destination, we have LEU source. Most of these ones are going to control like multiplexers. Others are going to control enables from our registers. And this is memory to register, register write, memory read, memory write, branch, and our famous LAU P1 and LAU P0. This controls the LAU. This are get sent to the LAU control unit. So how does all this make sense? Well, we could easily draw our data path. However, I think I might be able to copy it from somewhere else. Let me see. I think I'm just gonna go ahead and write and sketch it real quick. So this is what we have. So this is the sketch, our MIPS processor. This is the data path. All the signals that are right here, they come directly from the controls. So they're just wires being routed all over the place. So the way we're gonna implement this is very simple. We are gonna use a ROM, and the ROM will allow us to be able to code all of this very quickly. So we have OP5, OP4, OP3, OP2, OP1, OP0. And we have the different signals, the EST, register destination, LAU source, to write, memory read, memory write. For the first one, we have all zeros. That's for our art types. We want once 1 0 0 1 0 0 0 1 0 for word 1 0 0 0. Our stored word. It's gonna be, I don't care about that one. I don't care. And then lastly, for our branch equation, now we have to divide this in fours. So 1 2 3 4, 1 2 3 4, and then we can see each group individually. So for the first group, I have to convert all of this to hexadecimal. So I have a 1, a 2, and a 2. 1 2 2 2. The second instruction is 0, F, 0. Third, 0. I want to be a 0. It doesn't matter. You just need to pick one. and then 8, 8, and then for the for instruction 0, 0, 5. I just realized while sketching this to go up. I think I made a mistake. So this doesn't go to my control unit. That goes to my LAU control. And that's my functions file. Because if you see, these are my functions. That depending what type of LE up I sent, then it will read my function, because this only gets read if I have R types. So now that we have this programming, this is the little program that we have, we're able to implement that on Logisim. And the way we're gonna do that is by dropping a ROM. So we go here, we drop the ROM. 1, 2, 3, 4, 5, 6 for my input. And then for my outputs, I need 1, 2, 3, 4, 5, 6, 7, 8. I need 9 for my outputs. Then inputs, I'll put my output here. That is 9. And now we are able to start finding the programming. So for my address 000, I need 1222. You see, I have an output 1222. So for my next one, I have 10 and 3, and that one is 0F0, 0F0. For my next instruction is 10, 10, 10, 11. And that's gonna be 0A8. And then for my last instruction is 000 100, 0 100, and that's gonna be 0005. So now, depending my address, I got a 12222. You can also see the individual lines. If I split this into binary at the end, I think that's what we have to do, because we need all the individual lines that we need. So I might have to use a splitter to separate all those lines. So I'm gonna change this to binary, and you can see you got the different outputs. And if I put 10, 10, 11, 10, 10, 11, I got 0, 0, 0, 8, 8, which matches 0, 1, as you can see, 0, 1, 0, 0, 0, 1000, and I have 1000 here. As you can see, we have implemented our control unit. Very simple. No need to stress about gate implementations. It's just pure microprogramming, and it helps a lot, and it will help us expand our project later on without much of a hassle. Well, now that I have implemented the control unit, we can start wrapping things up. Today we saw how a handful of bits can drive our entire data path. With our implementation using a ROM, microprogramming becomes straightforward and extensible. I want to say that in the next episode, we're going to start integrating the whole system together and see how our MIPS CPU coming to life. I'll see you then. If you found this helpful, hit like, subscribe, and let me know in the comment what instruction you want to see next, or like how if any improvement do you think it would be better. Well, thank you so much. Bye.